Rama, are you chairing this session?
Avinash?
Hello, can you hear me?
Yeah, you can start the session.
Okay. So, good morning, all. My name is Avinash. So, today I'm chairing this session. So, the first talk is a contributed talk in this session, which is by Soumya Ranjan Ratha. Soham Chandra from Presidency University, India. So he will present his work on effect of a uniform random external field with spatiotemporal variation on compensation in Ising spin 1/2 tri-layered square ferrimagnets. So Soham, please, you can share the slide.
Good morning from India, Dr. Madhu. I think I am clearly audible.
Yeah.
Okay, so let me share my screen first. Is my screen perfectly visible to everyone?
Please go to slide show.
Yeah, full screen. Yeah, fine.
This is in presentation mode, so I think that now it is fine. Is it so?
Yeah. Now
Okay.
you can proceed.
Good morning from India. I am Soham Chandra, a doctoral student of physics at the Presidency University, Kolkata. Before I start, I would like to thank the organizers of IEEE Magnetic Singapore chapter for 2023 for providing me this wonderful opportunity today to present my work on effect of a uniform random external magnetic field with spatiotemporal variation on compensation in Ising spin-half tri-layered square ferrimagnets. So let's introduce the topic first. Magnetic refrigeration is more than a century-old subject, but with its promise of making new materials for energy-efficient cooling devices, a renewed interest is seen towards the research on magnetocaloric effect. But layered ferrimagnets, which show compensation effect, are rarely used as magnetocaloric material compared to conventional second-order transition materials. Magnetocaloric effect is basically heating or cooling a magnetic material with the variation of applied magnetic field on the bulk. A recent 2D triangular Ising engineered structure by Britton and his co-workers with penning-trapped beryllium atoms have shown us that they are indeed a promising subject or model for ferrimagnetic uh, magnetocaloric materials like the ones used in this study. This study may become a reality as figure 1 shows us. This is indeed an added incentive for the numerical studies. So figure 1 at right shows the tri-layered magnetic material of our simulation. Each of the three alternating layers are composed completely by either A or B type of distinct theoretical atoms. They are endowed with spin value half with mixed type Ising like nearest neighbor interactions between like atoms, that is between A designated atoms and between B designated atoms. the interactions are ferromagnetic. Similarly, between the unlike atoms, that is between A and B, the interactions are antiferromagnetic. So we land up at a ABA trilayer using ferrimagnet. In figure 2, this is a miniaturized version of the system that is used in the simulation, where in the real simulation each plane has 100 by 100 sides on a square lattice. Moving ahead, the Hamiltonian on the slide is used for simulation. First three terms are intraplanar ferromagnetic terms for the top, bottom, and the mid layers respectively, whereas the fourth and fifth terms are the interplanar antiferromagnetic terms, and the sixth term is basically the spin field interaction term. As I said just now, intraplanar ferromagnetic terms have the coupling constants JAA and JBB greater than 0, that is positive, whereas the interplanar antiferromagnetic terms have their coupling constant JAB negative, and the sixth term, which has HI in it, is basically the external magnetic field at site I at time instant small t. In the simulation, we have used Metropolis single spin flip algorithm with the controlling parameters being the ferromagnetic ratio, that is JAA by JBB, antiferromagnetic ratio, that is JAB by JBB, and the local field HI, which is basically drawn from a uniform random probability distribution. The mid-layer coupling strength, that is JBB, is basically the dominant one and is taken to be equal to unity in this case. Let's see, when there is no field in the system, how the system behaves as we change the temperature of the bulk. So we have two distinct scenarios. In figure 3, with the black curve, which is actually the total magnetization of the bulk, we find 2 points along the temperature axis where there are jumps from zero magnetization. The farthest one is basically the traditional critical point for a magnetic system, but the one on the lower end is the compensation point. Here the ferromagnetic coupling ratio is fixed at 0.5, whereas the antiferromagnetic coupling ratio is fixed at minus 0.1. We understand that compensation is basically a bulk phenomenon, and because of non-zero interlayer antiferromagnetic coupling and individual layers, the bulk and individual layers both have actually same critical temperature. When we increase the antiferromagnetic coupling ratio to 1.0, so basically there would be a negative sign before 1.0 as it is the antiferromagnetic coupling ratio. So the strength is increased, whereas the absolute value in the traditional mathematical nomenclature is basically decreased. So the compensation point actually disappears. So in figure 4, we find that compensation basically depends on the values of the individual coupling ratios, that is JAA by JBB and JAB by JBB. So a suitable choice is actually necessary to find the compensation point in such a system. So moving ahead, let's discuss about the external site dependent magnetic field, which is now switched on the material after, which would be switched on the material after equilibration. So the field, the external field, obeys a uniform random distribution. So if the standard deviation is sigma, then the probability is same for choosing any value within a designated limit, that is between root over 3, that lies between plus minus root over of 3 sigma, and the probability is basically same for all the values within this interval, which is equal to inverse of root over of 12 sigma, and it is 0 outside that interval. It's quite common. It's quite common for all of us.
Yeah, so 2 more minutes.
Okay. So additionally, the time average of the bulk average is also 0, with T naught being the instant of switching on the field and delta is the exposure interval for the system in the field. Also, the time average of the local field is 0. So now the pertinent question is, how do we measure time? So one Monte Carlo sweep of the entire lattice, that is 3L square random single spin flips, actually constitute unit of time. A few definitions here are in order. So we can clearly distinguish that the first one is for sublattice magnetizations at any time instant small t, where the sum is over all spin orientations on a particular plane. Here small q stands for the top, mid and bottom layers as and when needed. And the second one is how the time average is calculated, with T naught and delta being same as before. Now comes the important one, the dynamic order parameter. It is basically the total magnetization time averaged of sublayered magnetizations of the top, mid and bottom layers. So these are the two plots of order parameter versus temperature. So in figure 7 at left, we see compensation is present when there was no applied field. Please see the purple curve. But for all the non-zero values of the field, compensation is destroyed. And even the magnetization at the lowest temperature is affected. In figure 8 at right, when the antiferromagnetic coupling ratio is decreased from minus 0.04 to minus 1.0, we see the system shows compensation for zero and non-zero fields, but the magnetization of the bulk at the lowest temperature and the nature of evolution actually changes. So what happens when the field is applied within the system? So we see that in the top portion of figure 9 shows the bulk average of field versus time. After the system equilibrates with no field at T naught equal to 50,000 MCS, the sublattice magnetization start to react. The
1
surface
minute.
areas are mostly affected, and for sigma equal to 1.0, the sublet
Just 1 minute.
Okay. So I am
just
quickly winding it up. I'm quickly winding it up. So mostly so surface areas are mostly affected, and for sigma equal to 1.0, you see that the sublayered magnetizations actually approach the zero value. That is, the magnetic ordering is nearly destroyed. So just one more slide to understand what is happening here. So the spin density plots are shown here. So what we see that the lattice morphologies clearly tell us that the vanishing of magnetic order in the surface layers with sigma 1.0 is basically a manifestation of what the external field has done to the system. So we see that where the in-plane coupling strengths are weaker, that is in the surface layers, the magnetizations are mostly affected, and in the mid-bay layer, where the coupling is the dominant, the ferromagnetic in-plane coupling is the dominant one, there the magnetic ordering remains almost unaffected. So the conclusion is basically is included in the slide. So what we see is that as we increase the standard deviation of the field, we see that the compensation in the phase diagram, we see that the no compensation islands actually, the area of no compensation islands actually increase, and the nature of increment is basically a superlinear one. So we find that basically a scaling of the area of no compensation islands exists with a scaling exponent of 1.95 plus minus 0.12. So with this, I would like to conclude right now. This talk is based on reference 3, and in this list, a few more references are here for certain technical aspects. So at last, I would like to thank you all for your attention and wish you all a very good day ahead. Thank you.
Yeah, thank you. So now the talk is open for quick questions. Any question? Okay, so I have one question in slide number 12.
In slide number 12, please allow me to go to slide number 12. Here we are.
Yeah. So the left curve where you saw OT versus T, right?
Yes, it is OT.
So,
OT is the order parameter and T is the temperature.
So for purple curve, you have a starting point is lower, but for other values, like it's almost like stable, and after a certain temperature value, it drops suddenly. So what is the physical phenomena happening behind this?
Yes, if I get your question correctly, then I would like to say that the lower values, that is what is basically you are seeing in the panel. So the purple one, which has a jump across the zero magnetism, is basically for the field free case. Okay, so what we see is basically that we do have another point on the temperature axis where the system reaches zero magnetization other than the critical point. Okay, so that is basically the compensation point that I was talking about in this talk. So what happens is that when we increase the standard deviation of the external field, what it does is it destroys the magnetic order in the surface A layers of the ABS structure. So when the surface A layers are almost randomized, what will happen? That only the mid B layer shows the temperature evolution of a particular ferromagnet that we every day see. So what you are getting to see at about sigma equal to 0.76 or rather sigma equal to 1.0 is that only the B layer reacts to our conventional ferromagnet, and the surface A layers do not actually react with temperature. That is actually the temperature evolution gets destroyed by the application of the external field.
Okay, thank you. So if no other question, let's thanks to the speaker and then move to the another contributed talk, which is now we can answer the slide. So which is by Soumyaranjan Rata from Akita University, Japan. So his title title is Reducing Magnetic Damage in Bismuth Ferrite Based Thin Film Microfabrication, Optimizing Etching Parameters. So please share your slides.
Am I audible?
Yeah, can you?
My slide is moving, right?
Yeah, it's fine.
Yeah, thank you very much. Okay, I'll start.
Yeah.
Hello everyone, I am Soumyaranjan Ratha, PhD scholar of Akita University, Japan. I am going to talk about reducing magnetic damage in bismuth ferrite based multiferroic thin films during microfabrication by optimizing etching parameters. So before going to the work, the motivation behind my work is like, in the case of magnetic memory device, we write data by using spin current. Also in the case of STT-RAM, we write data by using spin current. If I talk about some optical devices, for example here, special optical modulator. Here also we write data by using spin current. And writing data by spin current consume more amount of energy. If we think about magnetic sensor devices, for example, hard disk drive, in the case of GMR, the output signal is not so high. So to solve these two problems, one is energy consumption and another is the signal output is not sufficient, we have to modify the devices. So let's think about one idea, that is multiferroic material. As we know, multiferroic material exhibit more than one ferroic properties in one phase, and these are mostly perovskite structure. Here I'll be considering bismuth ferrite perovskite structure because it has spontaneization polarization along the diagonal, and here I will not be worried about the temperature because it shows ferroelectricity and ferromagnetic in room temperature. And one problem is there that it has antiferromagnetic G-type structure. But by substituting some elements from some proper element, we can enhance its magnetic property as well as electric property. So this is a small schematic diagram how we can use this multiferroic thin films to reduce the energy consumption. You can see in the case of pink part, it represents the multiferroic thin films and we have electrode. As we know, in the case of multiferroic material, the ferromagnetization vector and ferroelectric vector are interlinked by magnetoelectric coupling. So by changing the direction of the ferroelectric, the magnetization will also be switched, which we can achieve by changing the voltage difference. So as a result, we could reduce the writing current that will lead to very less electric consumption. And here the cost is very simple. We are not using any noble material like we use in the case of hard disk drive. And we are not using a noble material. So considering all into account, we can use this material to reduce the energy consumption. But for proper application, for example, I want memory device application, then I will be expecting the material having high saturation magnetization and high perpendicular anisotropy. For optical devices, I need core rotational angle and high perpendicular anisotropy. For sensor devices, I need low coercivity and high saturation magnetization. So we fabricate our thin films by using pulse DC reactive sputtering with very high frequency plasma irradiations. This is similar to all sputtering machines, so I'm not going much into the sputtering part. Only one part I will say here, we use VHA plasma, which really enhance the crystallization of the thin film by enhancing the magnetic property. In our first trial, we substituted barium and we could enhance the magnetic property. As I said, the pulse DC could increase the magnetic property. So this is very clear that in the case of pulse DC, we could increase the magnetic property at a concentration of 40 to 60 atomic percentage. And this is the signature of the enhanced magnetic property. But here again, two problems, that the Curie temperature is not so high, and this showed in plane magnetic anisotropy. As I said, I need perpendicular magnetic anisotropy. So after that, I substituted so many lanthanoids in A site with cobalt concentration in B site, and I could achieve, in the case of neodymium substituted bismuth ferrite, very high saturation magnetization and very high perpendicular magnetic anisotropy. So this material is better for the memory device application. In the case of lanthanum substituted bismuth ferrite, I could observe very high core rotational angle and of course very good saturation magnetization. So this is better for the optical device applications. In the case of europium substituted bismuth ferrite, the coercivity is so low and the magnetization is so high. So I can use this material for magnetic sensor devices. By playing with so many elements, finally I could come with three important material for device applications. So if we think about the perpendicular magnetic anisotropy, as I explained before, I check the perpendicular anisotropy by CF Stoner-Olpert single domain particle. By changing the angle between the thin film and the external magnetic field, I could see here that it is achieving a perpendicular magnetic anisotropy maximum at 90 degree. That means it shows PMA. And this neodymium substituted, as I said, this is better for the memory devices, and here also I showed that it has very good PMA, so I can use in the memory device applications. So in this study, I'll be showing now, I could fabricate three material. Now, are they really suitable for the device applications? Because we know the domain size and grain size should be very small. And in the second case, as we know, in the case of a micro fabrication, we will expect some magnetic damage. So in this case, I will be showing what is the suitable etching process to minimize the magnetic damage. So first I considered these three elements. I measured their domain size and grain size. I could see their grain size is lying in between 50 to 100 nanometer and domain size is around 150 nanometer. That is very small in the case of multiferroic thin films. So this is suitable for the device applications. If I think about the Curie temperature, which I observed very small in my previous slide. So here you can see in my new materials, this is around 450 degrees Celsius. That is also very high for the device applications. So considering these two basic parameters, I can say that this samples suitable for the device applications. So now very important part, that is microfabrication. To study the magnetic damage during microfabrication, we considered our thin films and we fabricated micro dot of 3 micrometer. So you can see this dot area is covered with resist pattern, and this out of dot area is simply bismuth ferrite film. So when this thin film with dot is exposed to etching gas, the dot area is covered. That means the dot area is safe, but out of dot area is no safe. So etching is going in the out of dot area. So if I can compare the magnetic property between on dot and out of dot, and there is some change in magnetic characterization, then I can say there is more magnetic damage. So for this, you can see in the left side, I did a reactive ion etching with CHF3 and oxygen gas, and in the right side, I did dry etching. But when I checked their phase difference, there is no change in the phase difference, but only from the phase difference, I cannot say that there is no magnetic damage. To confirm it again, I considered the change in domain size and grain size study. So in the case of the first one, that is, okay. In the case of reactive ion etching, I could find there is no change in the domain size and grain size, but in the case of dry etching, there is an increase in domain size in the case of a dry etching, that is leading to the magnetic damage. To confirm it again, I check the change in coercivity, and I found in the case of a dry etching, there is a drastical change in the coercivity, and this is studied by the micromog measurement system. And here also I found that dry etching is giving more magnetic damage, and I found that RI is not giving magnetic damage. Then I found that in the case of oxygen presence reactive ion etching, there is very small change in the grain size and domain size, but in the case of without oxygen, there is a change in the grain size and domain size. That means in the presence of oxygen, the etching process is good. To confirm it again I checked the change in coercivity, and I found when there is etching in the absence of oxygen, this is giving a huge change in the magnetic property, but in the presence of oxygen, there is almost no change in the magnetic property. To confirm this, I came for the XPS study to study the oxygen vacancy. So I found in the case of bare material, when there is no etching, the oxygen vacancy is 27%, and when this is in the presence of oxygen, it is giving oxygen vacancy of 60%, and when it is absence of oxygen, it is giving very high oxygen vacancy, that is 79%. And here oxygen has a very big role in creating magnetic damage. And here I concluded that in the presence of oxygen, if I am performing my etching, this is giving very minimal magnetic damage, and that is very good for the device applications. So this is the summary of my work, whatever I presented. In the next work, we will be optimizing the dry etching. So thank you very much for your presence, and thank you very much for my collaborator from Osaka University and NIMS.
Yeah, thank you for the talk. Now the session is open for questions. So any question from audience? Okay, so I have one question. So
Yes.
for the multiferric system, you are using a single phase. So whenever you actually try to improve the magnetic property, you always have to compromise with the ferroelectric property. So
Yes.
how to overcome this kind of problems when you are doping different elements?
Okay, so I can show you the ferroelectric property. You can see in the case of a neodymium, I said neodymium is my candidate material, and also europium is my candidate material, and one more candidate material is lanthanum. In all the three cases, I am getting some not so good, but the ferroelectric property is good. So here both cases is being optimized actually.
And both are increasing.
Yes, both are increasing simultaneously.
Okay. So what is happening in the lattice?
Lattice, actually we find more oxygen vacancy, but here we are introducing more oxygen during fabrication by putting more oxygen in the target.
Okay.
That's why there is no leakage current actually.
Okay, thanks. Any
Thank
other
you.
question? Okay. If not, yeah, you can just answer. So our next talk is a keynote by Professor Subhankar Vedanta from NISA, Bhubaneswar. So he will talk about antiferromagnets for spintronics. So Professor Vedanta, please share the slide.
Yeah, good morning. Just trying to share.
The presentation mode. Yeah, can you see the slides?
Let's see here. Just a second. Okay, a second. Okay. Do you see my full screen now?
Yeah.
Okay, great. So, thank you so much for the kind introduction. So, good morning, everyone. My name is Subhankar. I'm working at the National Institute of Science Education and Research, known as NICER, in Bhubaneswar in India. So, first of all, let me begin with thanking the organizing team for this very kind introduction and also organizing such a nice conference, which has many interesting topics and talks. So, it's really nice to be here. So, today I will be talking about antiferromagnets for spintronics, or briefly known as antiferromagnetic spintronics, and I will show some interesting candidates which we have pursued from the family of antiferromagnets. So let me just first say where is Bhubaneswar, because some of you may not know. This is in the map of India, and we are exactly at the east coast or the eastern part of India. So Mumbai is here, so you can see it's just opposite side, and New Delhi is there. So and Chennai is here. So it's like, you know, diamond, and we're exactly at the eastern side, close to the Bay of Bengal. And this city is very historic, has a lot of interesting things. This goes down with the history to the Kalinga War, where King Ashoka made war with the local people in the state of Odisha, and a lot of people were died, nearly 300,000. This is going back to like 2,200-year-old story. And then he changed his mind and started spreading Buddhism in the world. And to commemorate that, this famous temple has been constructed in the city of Bhubaneswar by the Japanese people. And the city or the state of Odisha has a lot of interesting things to offer. Like Bhubaneswar is known as the temple city. Also, the Sun Temple in Konark is very close by, which is a historic architecture, and it's now one of the World Heritage in Odisha. And the Chilika Lake is, I think, the largest lake in Asia. And there are other interesting things, and particularly last few years, Odisha is seen as the hockey capital of the world. So in case you are around, please let me know. I would be happy to host you and show you around. This is our campus. We have a small hilltop. There's a meditation center. If you go there and take a picture, you get the bird's eye view, which looks like that, with the different academic buildings. And I am actually precisely in this physics department, and office is somewhere here. And we have a very big 300-acre campus, and having undergraduate, graduate education or courses for the students. So before I go to the talk, I'd like to thank my excellent collaborators. So very motivated masters, PhD students, and then some postdocs. Also, I'd like to thank collaborators from different parts of the world, which have been very generous in helping collaborating with us, and the different funding agencies. We are an experimental group, so we continuously need financial support, and I thank various funding agencies for their generous support. This is a quick glimpse of our laboratory. We started about 10, 12 years ago, and it's a very young institute. We have a couple of deposition systems for metals, semiconductors, organics. Then we have the pulsar deposition for manganites, oxides, based materials, laminates, and so on. A few characterizations like FM, X hat D, Raman, TM, SEM, then a few transport properties like here, then low temperature magnetic force microscopy, which is recently added. We also do spin dynamic study by ferromagnetic resonance and perform the ISHE. So today's results will be primarily on that, where we show the spin to charge conversion with different quantum materials. And for today's talk, I have chosen the antiferromagnets. We also do lithography, and major focus of our group is magnetic domain imaging, Skyrmion imaging, and so on. So the point is, I think to this audience, I don't really need to introduce what is spin orbit torque, but in a glimpse, assuming there are young students. So the current hard disk technology employs magnetic field, of course, locally, to write information into your device using the giant magnetoresistance resistance principle. However, this consumes a lot of energy and has certain drawbacks, joule shifting, and so on. Now, to overcome that, it is proposed that we take more efficient devices, and in that context, the spin orbitronics or the spin orbit torque-based devices are much more less power consuming, where the idea is not to employ any magnetic field, rather you take a like a current-based device. For example, you can say that this block is like one component, is something with high spin orbit coupling, and if you pass a charge current, then due to some quantum mechanical phenomena, you can imagine the electrons of opposite spin will go to the opposite edges of this block, and that will lead to like a spin current. And that spin current can apply a torque on this tunnel junction, where we can play around with this free magnetic layer. And depending on its orientation, which will be either parallel or anti-parallel to the magnetization of the reference layer, which is another ferromagnetic layer, where the spin is or the magnetization is more or less fixed. We can use it as a hard magnetic layer. You can fix it using exchange bias. That means you can deposit an antiferromagnet. And basically, the idea is if you change the magnetization orientation of this bottom layer, you can define parallel and anti-parallel orientation. Basically, you can read it at 0 or 1, because when you read it, it will give you less or high resistance, which you define as 0, 1, just like in the GMR. Okay, but the whole difference to the current technology is you don't employ any magnetic field. That's the most significant difference. Now, as you see, these kind of systems has basically two components, and you need to ask few questions like what is the best material to make the this charge to spin conversion using spin orbit coupling. Obviously the heavy metals like platinum are the most preferred material because they exhibit high spin orbit coupling, but we don't want devices made of platinum for obvious reasons. So people are looking for other alternatives, and that is one interest. And other questions are like, how do you write this information? And yeah, so this is basically, let me maybe go here. So how do you write the information in terms of magnetic domains or skyrmions? And you need to understand the skyrmion dynamics, domain dynamics. In that respect, you need to explore new type of ferromagnets which will exhibit low damping, high saturation magnetization, and so on. And yes, is there a question?
Your voice is breaking.
Voice is breaking. I'm sorry. Is it now better?
Yeah.
Okay, I will stay close to the computer. Thanks. So the point is, you need to make the smaller size of the information carriers, or like domains or skyrmions. So there are certain questions we ask and try to formulate. So as I said, this basically goes to the spin Hall effect. You might have already heard. Now, to find out what are the best suitable materials for the spin to charge conversion or charge to spin conversion, you need to rely on the spin Hall effect. However, it is very difficult to measure the spin Hall effect directly. You can do that by magnet optics principle to measure the spin current, but it is not very direct. It is not very straightforward. However, people discovered that you can just take the reciprocal of spin Hall effect, which is known as inverse spin Hall effect, assuming you have created already a spin current, and if you pass it through high spin orbit coupling material, you will be able to generate the Hall voltage, and you can calculate the spin Hall angle, which is the ratio to spin to charge current, or vice versa. And we are looking for materials which can exhibit high spin Hall angle for efficient charge to spin conversion. Now, as I said in the beginning, in this kind of spin orbit torque based device, it is like two components. The bottom component is the high spin orbit coupling material, and the top component is the ferromagnet. So you can define the system like component A, component B, where, as I said, the component A is something with high spin orbit coupling, and we are looking for alternatives, and these alternatives are other heavy metals also, like tantalum, tungsten, and so on. And you can create these beta phases, and they exhibit even high spin Hall resistivity and spin Hall angle. Or you look for other possible quantum materials. In that respect, topological insulators come into rescue. They exhibit very interesting properties, and they have this spin momentum locked surface states, which can exhibit high spin orbit coupling. Or antiferromagnets, because we have a lot of antiferromagnets, and most of them can exhibit basically high spin orbit coupling. And the antiferromagnets have other advantages too, but for the spin to charge conversion, you can use it as a good material. And of course, also there are other possibilities like transition metal dichalcogenides like MOS2, MOSC2, and so on, or 5D oxides like iridium oxide, ruthenium oxide, and so on. So the ferromagnetic part, we exploit quite a bit of domain physics, domain model dynamics, Scormion physics. And you can do this domain engineering with various approaches using dots, anti-dots. So here I just quickly give one slide summary to some of our work in the so-called superferromagnetic domain state in magnetic dot arrays, where you try to just couple them with dipolar interactions. And you see, even if the dots are completely isolated, but still due to the dipolar coupling, you can have simple ferromagnetic like correlations. Like in this case, the dot arrays are like a percolating. So there is direct exchange interaction between the dots because they are kind of touching to each other. And you see beautiful hysteresis loop. You see these kind of ferromagnetic domains where many particles switch together. However, in this system, the dot arrays is absolutely isolated. There is no exchange interaction and just dipolar interaction, but you still see this hysteresis loop. One can, of course, argue that this hysteresis is coming from the individual dots, but that's not the case because you see the magnetic force microscopy image where you see multiple magnetic dots are coherently switching. So this basically leads to some kind of correlations among them, which you call them a superferromagnetic domain. Some people call it dipolar ferromagnetism, but it's basically the same. So we are studying, and you find some of the publications here. Similarly, we also study, the anti-dot arrays. Basically, it's like holes in a biscuit. Is a very popular biscuit in India, where you see these kind of holes, and the company claims by making such holes, you can actually radiate, or evaporate the humidity, so the crispiness of the biscuit remains better. So similarly, I mean, you can use defects because usually we believe defects are bad, but you can use defects and to improve certain properties. So the point is, this photo was taken in Chennai. I think there was a huge flood some years ago, and you see this gentleman is trying his best to go on the available little road. So just imagine this is a magnetic film, and these potholes are basically like periodic defects which you can design. It can be, of course, any shape, circular, triangular, like cube, or anything. You can do it on different lattice shapes. But the point is, if you make these potholes or defects smaller and closer, you can basically engineer the magnetic domains, and that's basically shown here. Maybe this video doesn't work. That's a sad thing. Okay, so this is a ferromagnetic domain in a continuous thin film, and you see huge magnetic domains. I'm sorry for the small scale, but it's like 100 micron. But now if you take a same film and you just dig, these holes, or these tangles are basically holes in the continuous film. Now you see the domain size becomes smaller, and that is basically domain engineering via these antidotes, and that's very, very interesting. And we have done much work, and there's a student who did his PhD on these magnetic antidote arrays, and there are several papers from our group on this. Now we are also working on skyrmions and skyrmion dynamics. Here, the point is, if you design your architecture in such a way that you have strong Gylon-Schemura interaction at the interface, then you can, induce the skyrmions. Of course, there are other methodologies existing too, and you can, start with the Lyapunov domains, and you can break into skyrmions by applying some field. Obviously, there is a high interest to look for zero field skyrmions at room temperature. These are all room temperature, and we found that we could achieve very small pinning landscape in our cobalt iron boron film, which was published recently, and you can actually have a very low critical current density. To the best of our knowledge, this is probably the lowest in the literature, and one is to explore more, and you can see some publications where we report our work on skyrmions. Now, we also work on various interface effects, and this is like the biryani physics. I say, if you are a fan of chicken biryani, the chef prepares the chicken and then puts a slice of chicken, then rice, then again chicken rice, and warms it for some time. The flavor of chicken goes inside the rice, and you can feel that the rice tastes like chicken. So that's basically the interface physics, where you take a ferromagnet and you measure its magnetic property, and you deposit a non-magnetic or diamagnetic organic semiconductor on top of it, and you expect no change in magnetic properties. That is obvious, but however, you can also imagine that there will be some changes at the interface due to whatever hybridization or charge transfer and so on, and some kind of proximity effect, and that called as the spin interface. And it can be better visible here, where you have a ferromagnet and you see the density of states at the Fermi level. Now there is an organic semiconductor. As I said, these are non-magnets, so you have nothing here. But let's bring this organic semiconductor or the molecule on top of the ferromagnet, like shown here. Then you see immediately there is an opening around the density of states. So this shows that the organic semiconductor, which was non-magnetic, is becoming ferromagnetic. And you can even change the basically the ferromagnetic property by having different alignment. This is like vertical, this is like tilted. So this is a very interesting emerging field, although very young, that you can basically create magnetism in organic materials, and that leads to much added functionalities. And most importantly, this spin interface will modify your magnetization reversal, magnetic domains, magnetic damping, and so on. Okay, so a very, very interesting research work, and it also invites many other organic semiconductors. And in our group, primarily we have worked on C60, but also we're looking at other organic semiconductors. And this is just one example that how you can make engineering of magnetic domains. Let's say this is a platinum cobalt thin film, where the bubble domains are primarily observed. But when you put a thin layer of 660 on top of this cobalt, you see the domain size is getting very, very small. I mean, on the right side, if you could see these small like dots, they're actually ferromagnetic domains on the same scale. So without C60, you have these huge bubble domains, but with C60, you can make this domain engineering. This is another approach, like antidote arrays. Okay, so we have recently reviewed an invited perspective where you saw the emerging concepts related to organic spintonics, and if you are interested, you can look at this. And very recently, we have also shown that although C60, which consists of carbon atoms, and carbon atoms are primarily low atomic number elements, and you don't expect much spin orbit coupling, where Z, the spin orbit coupling is primarily proportional to Z to the power 4, where Z is the atomic number of the element. However, it is possible that because of the curvature of the fullerene molecule, it's like a football structure, you can also induce some amount of DMI, and that is something we have quantified recently. It's not very strong though, but nevertheless, it's not zero, and maybe in future we can further work on it to optimize the DMI.
5 more minutes.
Yeah. So now let's talk about these different materials for spin to charge conversion. As I said, the primary requirement is high spin orbit coupling. Now, in our group, we mostly look it through the inverse spin Hall effect. So basically, the protocol is you put your sample on a flip chip way on the coplanar waveguide, and you pass high frequency microwave field. You basically pump energy to it. Now it generates a spin current which goes through the ferromagnet to the high spin orbit coupling material. Here it's called non-magnet. And then you basically develop a voltage which you can measure, and here using a nanovoltmeter. So basically the black curve is the ferromagnetic resonance spectra, and the blue curve is the ISHE voltage. If you disentangle, you can figure out the symmetric and asymmetric voltage, and you can measure angle dependent measurements to quantify different spin rectification effects like anomalous Hall effect, anisotropic magnetic resistance. But most important, the symmetric part contains the spin pumping voltage, which is our primary interest. And you can see how much is the spin pumping voltage with respect to the spin rectification effects. If it is more, that's good. And this is like a quick summary.
So, Prof, sorry to interrupt. Just 5 minutes. So please, yeah.
Yes. I noted your time.
Yeah.
I will wrap up.
Oh,
So,
yes, yeah.
This is like a summary where we are exploring different type of high spin orbit coupling material, where, as I said, like iridium oxide, ruthenium oxide, topological insulators, different kind of antiferromagnets, tensor metal dichalcogenides, and so on. We are also looking for alternative ferromagnetic materials, because usually you consider cobalt iron boron or permalloy, which are low damping materials, but we are also looking for the Heusler compound, manganites, and so on. Now, going quickly to the field of antiferromagnets. As you know, I mean, this is the famous lecture of Louis Nel. You have seen probably this slide many times, where people talk that Louis Nel thought that antiferromagnets are very interesting but useless. But obviously that concept has changed, and now antiferromagnets look very promising because of various aspects like terahertz spectroscopy, their zero stray field. And you can, and there, as I said, for our spin bombing experiments, they are very strong candidates as they exhibit high spin orbit coupling. Now, in a nutshell, you can say the antiferromagnets for spintronics are very, very interesting for exchange bias, for terahertz dynamics, spin to charge conversion, which I'm going to talk into next 2-3 minutes. Also, Nel vector switching, synthetic antiferromagnets, another interesting topic where you couple two ferromagnets and you can reduce the Fermion Hall effect, and so on. Now, broadly, antiferromagnets you can divide into collinear and non-collinear families, and I will show you some examples. Manganese gold is another is a candidate, of course, because it has very high Nel temperature, like 1500 Kelvin, and people have shown that it exhibits very nice properties with respect to terahertz spectroscopy, terahertz dynamics, and so on. Let me quickly go to our work, where we have prepared these manganese gold thin films in adjacent to cobalt iron boron thin films, which is a low damping material, and we could stabilize very nicely the stoichiometry of the manganese gold on MgO substrate, and you perform the the FMR and the inverse spin Hall effect. For the single layer, you get the damping like this, and when you put the manganese gold, so this is the single layer and this is the bilayer, you get an enhancement of damping that primarily due to spin bombing probably, and you perform all these detailed angle dependent ISHE measurements. From that, you could quantify that the spin bombing voltage was higher compared to the other spin rectification, and you also observe very high spin Hall angle. Then we looked non-corneliar antiferromagnets like manganese, gallium. And as you know, there are many candidates, for example, iridium 3 manganese, which has shown very high spin-Hall angle. So we started working on manganese gallium, and we could stabilize these, nice phase of the manganese gallium. Then we performed these like FMR experiments with ISHE. We got very similar, experiments where you follow the very standard protocol, so to say, to evaluate the spin bumping and the spin-Hall angle. And most importantly, we found the spin-Hall angle to be something like 0.52, which is very high spin-Hall angle in this manganese gallium. The last 1 minute, I would like to focus on a very interesting compound, or cobalt oxide. We know COO is a very standard antiferromagnet having Néel temperature about room temperature, and it's insulator, but we have prepared CO3O4 from a cobalt target by proper oxidation of the substrate, and we studied spin pumping of cobalt oxide by varying the thickness of this kind of ferrimagnetic CO3O4, and this shows the cross-sectional TM, very nice phase. And we performed the spin pumping, and we found the spin diffusion length to be about 2.5 nanometer by this analysis. I'm not going to details. I'm just summing up, where I would like to show that nice spin bumping has been observed, and the spin-Hall angle is very much comparable to like platinum. Okay, so it shows that CO3O4 is a very interesting materials. And finally, I like to summarize that this field of spin orbitronics has a lot of excitement still to see, where we can look at various ferromagnetic compounds for the domains fermion dynamics. We need to ideally study various quantum materials that includes antiferromagnets, obviously for efficient spin to charge conversion, and also we need to look the interface phenomena among such material heterostructures. So with this, I like to summarize. Thank you so much for your kind attention.
Thank you for the talk. And now talk is open for questions.
Thank you, Prof, for the nice talk. I have a very brief question. So, when you were discussing the results of the change in domain size because of the organic antiferromagnet. So, what does this carbon-based organic material does?
Oh, very nice question. So actually, I didn't have time to go to the details, but if you look those papers, what we say, or what even some other people have found, of course, they don't do much on the domain structure or magnetization universal study, but primarily this has been shown that there is this interfacial hybridization between the carbon and the ferromagnetic elements. Okay, and there is also some amount of charge transfer, because of which the carbon gets a magnetic movement. And let's say this picture, if you see, this is a kind of evaluated structure from the polarized neutron electrometry, where you see about 2 nanometer of C60 getting a magnetic movement. So there is a thin interface which has a magnetic movement. So it's like ferromagnet. So obviously it will have its own impact on the global anisotropy, global magnetization universal, and that leads to such kind of engineering of domain. So there is a change of anisotropy, and it also helps or kind of drags the magnetization universal process. I mean, you need to see some of the papers, but the bottom line is that the interface is getting magnetic, so it is modifying the global properties.
Thank you, Prof.
Yeah, welcome.
Any other question from audience? Okay, so I have one question, Prof. You got the MN2 AU work, so where you found the spin-Hall angle is 0.52. So, so if I compare with platinum, like in terms of resistivity and spin-Hall angle, how comparable is the MN2 AU spin-Hall angle with respect to resistivity?
Yes, very nice question. Thank you. So, I mean, for platinum, of course, as you know, there is a wide reported values, and the range is something like 0.02 to can be 0.3 or so. So I think the value shown here is much stronger than platinum, I would say. So and it's much cheaper. I mean, that's one thing, but I think the spin to charge conversion is happening very efficiently, and most importantly, because it's an antiferromagnet, it has other, as I said, repercussion like terahertz spectroscopy and so on. So to summarize, I mean, this seems better than platinum, I would say.
Okay. So, okay, thanks.
Yeah.
So, if no other question, let's
May
move
I
on.
ask a small
Oh,
question?
yes,
Prof?
yes.
Yeah, please.
I mean, continuing to the Avinash's question, did you also try switching I mean, to AU?
Oh, no, not yet. I mean, this is something in our to-do list. We like to do it, but so far we have only performed the spin bombing experiments through ICG, and that is published here. And we have now published recently a new paper where we explored the different phase of manganese gold. Okay, so you can also control the phase, but the switching is something we are now probably going to do it. This is very interesting, and thanks for asking this question.
Thank you, Prof.
Yeah, thank you. So now let's move to the another speaker, which is our keynote speaker, Prof. Chandrasekhar from IIT Hyderabad, India. So he is presenting the engineering spin orbit coupling via crystalline phase of heavy metals. So yeah.
Dr. Avinash, can you see my screen?
Yes, yes, yes.
Okay. So, yeah, so thank you very much, Avinash. And yeah, so I'm Chandrasekhar Murapaka from IIT Hyderabad. Okay, so first of all, I would like to thank the organizers for inviting me to give a talk here. So I would like, it reminds me fondly that in 2011 and 2013, I participated as a student for contributing talks and also in the competition. So yeah, thank you, Professor Prem, for inviting me. I mean, it feels so good to be here. And thanks to Ramu and Durgesh. So today I would like to talk about some of our recent work at IIT Hyderabad, that is on engineering spin orbit coupling via crystalline phase in heavy metals. So thanks to Professor Subhankar, the previous talk, he has given the complete overview of this spin orbitronics, and then so some of my the discussions and slides may be a little bit of overlap with him, but please bear with me. But I'm happy that he has already introduced many of this spin to charge conversions as to spin conversion. Okay, so yeah, so with this I would like to first before I move on to my talk, I'd like to thank a few people. So first of all, I would like to thank my PhD supervisor who introduced me to this Spintronics. So I did my PhD from NTU Singapore. So I would like to thank Prof. Yu Wensang. And these are the PhD students who have contributed to this work, specifically Dr. Sriram, who recently graduated, currently working as a postdoc at ISA Bangalore, and Dr. Vivekananda, who is currently as a postdoc at NTH Taiwan. So I'm discussing some of the works of these two students, and yes, I would like to thank one of my key collaborator and a friend, Dr. Arvinda Haldar, with whom we are able to perform this spin pumping experiments. So the outline of my talk, I will briefly discuss about spin orbit coupling, which has already been done by Professor Subhankar, and I will discuss about what are the implications and of the spin orbit coupling and how the spin orbit coupling can depend on the crystal structure of heavy metals specifically. Then I will discuss about two different works we have done. One is how to tune the crystalline phase of tantalum via sputtering growth rate, and also by using a different thickness of a seed layers, basically a crystalline seed layer such as nickel iron. And also then I'll discuss about how to tune the crystalline phase of tungsten via sputtering growth rate and sputtering pressure. I'll show you that what are the implications of changing this crystalline phase on the spin Hall angle via the spin pumping and inverse spin Hall effect measurements. Okay, so we all know what is spin orbit coupling. Basically, if you take a single atom, the spin orbit coupling, we know that electron has two angular momentums. One is spin angular momentum, second one is orbital angular momentum. And the coupling is LS coupling gives us a total angular momentum. However, I would like to make it clear that I'm not talking about an electron that is present within the atom. So the discussion here is about a free electron that is moving in a metal. And we all know that whenever there is a free electron, and then if there is a presence of magnetic field, there will be some Lorentz force that is it is going to experience. And a free electron that is moving in an electric field, we know that that electric field feels like a magnetic field. So we all know that electron is moving with a pretty high velocity, around 10⁶ meters per second. So in relativistic reason, the electron that is moving in a periodic potential, that feels like that electron is at a constant position, and all these positively charged ions are moving in opposite direction. So basically, electron thinks that there is a charge that is moving in opposite direction, which this electric field, because of the motion, feels like a magnetic field. So whenever there is a magnetic field, electron with two spins, up spin and down spin, they are going to behave in a different way. So this is called spin dependent scattering. So this effect is called spin orbit coupling. That is the crystal or the lattice is going to give us spin dependent splitting. So if there is zero spin orbit coupling, both spin up and spin down are going to behave in the similar way. Of course, when there is a finite spin orbit coupling, you can see there is a spin dependent splitting. So that helps us to split the spins of electron with two spins in opposite direction. So there are several implications and applications of spin orbit coupling, such as Professor Subhankar has already mentioned, that there is a huge spintronics field like skyrmions, chiral domain walls, spin orbit dark magnetic random access memory, and we can get Rashba states. As I am going to discuss today is about spin to charge conversion. Okay, so the opposite is also true. Like Durgesh has asked a question whether the switching has been seen. That is through charge to spin conversion. So today I'm going to discuss only one part of the spin orbit coupling, that is spin to charge conversion in ferromagnet and heavy metal heterostructures. So yes, what are the materials with sizable SOC? What kind of non-magnetic materials which I should use? So that depends on the spin orbit coupling, the splitting energy that is directly proportional to g to the power of 4. So obviously the heavy metals are the ideal candidates, and as Professor Subhankar mentioned, that platinum is not a cost effective thing. So in our study we have chose both tantalum and tungsten, and then both tantalum and tungsten, they can have two crystalline phases. So tantalum can be in BCC phase, or also it can be in a metastable BCT, body center tetragonal phase. Similarly, tungsten can be in BCC or it can be in A15 structure. So by tuning this crystalline phase, since you can see that the spin orbit coupling depends on the electron scattering with the lattice, and then lattice depends on the crystalline phase. So by tuning this crystalline phase, we will be able to tune the spin orbit coupling, and that helps us to kind of tune the spin Hall angle, which is a key parameter that tells us that how efficiently we can switch the magnetization with a small current. So what is the key motivation here, that if this is the current memory hierarchy and architecture, where you can see a CPU and this is the hard disk drive, where hard disk drive lacks in speed, but it has very high storage capacity. At the same time, the cost is low. However, we need a high-speed memory close to the CPU. So currently we are using SRAM and DRAM, static and dynamic RAM, which are charge-based devices. So even if the device is turned off, there is always a refreshing. The memory has to be refreshed. So there is a standby power that causes high power consumption and also heating issues. So what is the solution? So this should be the ideal future which we should be looking at. We have to replace this static and dynamic RAM with non-volatile spintronic memories. So when you replace this charge-based devices with the spin-based devices, due to non-volatility, there will be no standby power. So you don't need to continuously refresh the memory. That makes the whole architecture to be energy efficient and then less heating issues. Of course, I'm not the one who is starting to do this. We already have a spin transfer torque magnetic random access memory, as Professor Subhankar has already given the basics of it. So basically, it is a two ferromagnetic layers separated by a non-magnetic tunnel barrier, that is MGO. So you have a reference layer and you have a free layer. And by applying current through this, we can switch the magnetization by injecting the spin polarized current that is from reference layer into the free layer. And if you change the current direction, the reflected spins with opposite polarity can switch the magnetization of the free layer. And we all know the basic tunnel magnetoresistance phenomena, where the relative orientation can give us two different resistance states. When they are parallel, you get a low resistance that can be represented as 0, anti-parallel 1. But one thing that you can see here that the parallel and anti-parallel can show as 2 bits, and you can switch the magnetization just by applying current without use of magnetic field. And the commercial 1 GB STT RAM has already been produced by Everspin long time ago. And this helps us to give us non-volatility, fast switching, and power consumption can be less. However, there are still some issues with this spin transfer torque based magnetization switching, that you can see that when to increase the speed of the device, you need to apply larger current pulses, and you have a tunnel barrier which can cause the dielectric breakdown. So we are compromising on endurance. So there will be low endurance if you apply higher currents. And also, as you already can feel it, there is a shared read and write paths. So there is always a possibility of accidental switching. So we are also compromising on data loss. So basically we should not apply a very high current through this tunnel barrier. So we need to decouple the read and write paths. So the solution is to look beyond STT, and spin orbit coupling helps us in that. So you already understood that by applying a charge current through a heavy metal, we can generate a spin current that can switch the magnetization of the ferromagnetic layer. So you can do the reading as usual like STT RAM in a magnetic tunnel junction, but writing can be done through an in-plane current by applying a charge current that can be converted into transfer spin current that helps us for switching. Okay, so it is just like this penalty kick that you can see that by applying some spin, the ball can go to the net, right? So as the previous talk has already mentioned, the opposite is also true. When you apply spin current or inject spin current into the heavy metal, that it will also be converted into a charge current. So basically, as you can clearly see that the injection of the spin current converted as a charge current can be seen as a voltage drop across the thing. So basically, either of the methods can help us to find out what is the efficiency of the spin orbit coupling, which can be measured by a parameter called spin Hall angle, how much spin current that is generated as a function of the unit charge current, right? So our interest here is to find out how to tune the spin Hall angle in this case. So let me go to the first part of my talk. So basically we have used a magnetron sputtering technique to deposit our material. So we have chosen tantalum, and these are the parameters. And by using a AFM technique, atomic force microscopy technique. So now AFM, because of Professor Subhankar, is it antiferromagnet? I'm sorry. So this is atomic force microscopy. You can see that by creating a step, we could measure what is the thickness to optimize the growth rates, right? So what we have done is that by increasing the DC power, we have changed the deposition rates by keeping all other parameter constants like rotation rate, background pressure, and argon flow rate. Okay. So interestingly, what we have seen is that when we increase the growth rate of the tantalum to 0.17 nanometer per second growth rate, we see that we are getting a pure alpha phase, and above which from 0.2 to 0.22 nanometer per second, we are seeing a mixed phase, that is beta phase is getting nucleated. And in terms of nickel iron permalloy, which we have chosen because of its low damping parameter, and when we have deposited permalloy at a particular deposition rate, that is 0.1 nanometer per second, when we change the thickness, we found that we are seeing the crystalline phase only from 12 nanometer thickness. Up from 4 and 8 nanometers didn't show any crystalline phase. Okay. So now the interesting thing that what we have observed is that you can see this is the reference tantalum, which means that the tantalum that is deposited on silicon. But when we deposit the same tantalum on top of a seed layer, that is permalloy of 4, 8, 12, 16, and 20, different thickness of permalloy, interestingly, for the same growth rate, that is 0.13 nanometer per second, you can see that the tantalum that is deposited on 4 and 8 still show the alpha phase that is similar to reference sample. However, tantalum that is deposited on permalloy 12, 16, and 20, that shows there is a nucleation of beta phase. So the tantalum that is deposited above 8 nanometer shows mixed phase, below 8 nanometer shows or up to 8 nanometer shows the pure alpha phase. And we wanted to see that why this is happening. If you clearly observe, you can see that there is a shift in the 2 theta for the alpha peak. Okay, so basically when tantalum is deposited above 8 nanometer, we can clearly see that the lattice parameter here has reduced, which means that there is a strain that is coming at the interface between permalloy and tantalum. And it is obvious that permalloy can grow as a crystalline thing. So there is always a possibility of strain that can be there because of the lattice mismatch between the permalloy and tantalum. That has caused there is a change in the despacing and also the lattice parameter, right? And we wanted to see whether it is truly because of the growth rate or the seed layer, which one is effective. So what we have done, we have taken permolai of 8 nanometer and deposited tantalum of 18 nanometer by varying the growth rate. So you can see 0.08 nanometer per second to 0.13 nanometer per second in all the cases when we deposited on permolai 8, right? Irrespective of the growth rate, we are getting pure alpha phase. Interesting thing that we can see that when we take permolai of 12 nanometer, okay, even at 0.08 nanometers per second, okay, where the reference sample show pure alpha phase, however, here on permolai 12, at different growth rates, we are seeing a mixed phase. So we could conclude that it is not just because of the growth rate, not only the growth rate that affects the crystalline phase of tantalum. However, the seed layer can also get affect the crystalline phase, as you can clearly see here. That if at all you deposit on 12 nanometer, irrespective of the growth rate, it is mixed phase. If it is 8 nanometer, irrespective of the growth rate, it is alpha phase. Okay. And now we have chosen the spin pumping technique. So the introduction is already given by Professor Subhankar. So I'll quickly go. So basically ferromagnetic resonance helps us to find out the magnetization dynamics, and it works based on Landau-Diffris-Gilbert equation, where it talks about the magnetization precision around the effective magnetic field. So what we are going to do is that we are going to apply an external RF signal, right? And whenever the frequency of the magnetization precision is going to be equal to the external RF, there is going to be absorption. And that absorption can be seen as a signal of in the intensity as a function of the magnetic field. So basically, the first term in Landau-Diffris-Gilbert equation talks about the precision. And second term, this precision is not going to go forever. We know that there is always going to be some damping. So that the second term talks about.
So can you come closer to the?
Sorry. Is it okay now? Okay. So basically, we have used spin pumping technique for the spin current generation. So we have used a ferromagnetic layer, that is the permolai, and then we have kept tantalum. By magnetization precision, the spin current can go from at the interface, and then the transfer of the spin current can be seen as a change in additional damping. Okay, so you have a intrinsic damping, and then due to the larger precision because of the loss of the spin angular momentum, that can be seen as an additional damping. Okay, that helps us to find out the spin mixing conductance, which I will talk about later. So from the ferromagnetic resonance technique, we found out the frequency as a function of H resonance. We found out 4 pi m effective from the Kittel field, and the damping parameters were found from the line width field. Okay, so to find out effective damping, so we took permolai of 4 nanometer and then permolai of 4 nanometer with tantalum of 18 nanometer. We see that there is a additional damping that can be seen as a line width broadening. Okay, so I'm not going deep into that, but let me tell you that there is a parameter that is called spin mixing conductance that talks about the amount of spin current that is transferred from the ferromagnetic layer to the non-magnetic layer, and that can be found out from the additional damping that is coming in the ferromagnetic resonance spin pumping experiment. So for the alpha tantalum, you can see that the spin mixing conductance is around 8 into 10 to the power of 18, whereas mixed phase, which shows that higher spin mixing conductance. And as I mentioned, that we can also electrically detect the spin current through this heavy metal. So we inject the spin current, and by using the transverse, the spin current will be converted into the transverse charge current. By using the copper electrodes, we have measured the inverse spin Hall voltage. So as you can clearly see that whenever there is a ferromagnetic resonance happening, there is a voltage drop across our sample that tells us that the spin current that is injected into the non-magnetic material is converted into voltage signal. And to make sure that it is truly because of the inverse spin Hall voltage, as you can see, we have varied the magnetic field in both the directions, and you can clearly see that as we increase the magnetic field, the frequency at which this VSISH, that inverse spin Hall voltage, is found is increasing, and also the polarity of this signal has also changed when we change the magnetic field direction. That gives us a hint that it is because of ISH. And as previous talk mentioned, that it's not only it cannot be truly because of inverse spin Hall effect. It could be because of spin rectification effects also. So to decouple, we have fitted this data with symmetric component and asymmetric component, and we found that the majority of the signal is coming from the symmetric component. That tells that inverse spin Hall effect is there in our samples. Okay, and from there, by using this this inverse spin Hall effect, we found that the spin Hall angle in the alpha plus beta, that is the mixed phase, is 0.15 as compared to the single phase alpha. So it shows that mixed phase can give us a higher spin Hall angle as compared to the single phase alpha. So just to quickly conclude the tantalum work, so tantalum grows as a single phase when we grow on permolai of 4 and 8 nanometer, but it grows as a mixed phase when you go above 12 nanometer, which is because of the strain due to the lattice mismatch at the interface. Okay, and from the spin pumping experiments, the spin mixing conductance and spin Hall angle both are found to be higher for mixed phase tantalum as compared to the pure tantalum phase. So let me go to the second part of my talk, that is about tungsten. Okay, so why tungsten? Basically, in all three heavy metals that what we discussed, that is tantalum.
5 more minutes
Sure,
left.
sure, Avinash, I can finish in 5 minutes. So we have tantalum, tungsten, and platinum. The largest spin orbit coupling can be found in tungsten, and it is also compatible with microelectronics, and it has very high melting point. And our interest is to find out what are the process parameters that can affect the tungsten phase, and is it really thickness dependent? And there are some reports says that beta tungsten cannot be stabilized above 5 nanometer. We wanted to see whether we can do it and finally find a structure and spin Hall angle correlation. Okay, so here we wanted to work with argon pressure. So as you can see here, when we change the argon pressure in our sputtering deposition, the deposition rate did not change much. And when we increase the power, it is almost a linear increase in the growth rate. Okay, so we have changed the argon pressure, and interesting thing what we have seen, that when we argon pressure at a constant deposition rate, right? So that is we fix the power of DC to and sputtering to 60 watt. 3 milliliter, 4 milliliter, 5 milliliter, we are getting a mixed phase tungsten, above which we are getting a beta phase, pure beta phase. Okay. And we have taken the thin film surface, and then we found that the roughness is increasing when you keep on increasing the pressure, background argon pressure during the deposition. So this can be understood because when we are increasing the argon pressure, the mean free path of the tungsten atoms that are getting sputtered towards the substrate, it is going to decrease. So when the mean free path decrease, the kinetic energy also decrease. So it prefers more like an island growth that increases the roughness. And that is also cause for getting a beta phase, which is a metastable phase as compared to the mixed phase. And we have measured the resistivity, and we found that mixed phase has lower resistivity as compared to the beta phase. And you keep on increasing the pressure, the resistivity is also increasing. And we wanted to see that how it depends on the deposition rate. So at a constant pressure of 4 milliliter, when we vary the growth rate, and you can see that the resistivity of this mixed phase is coming down, which tells us that when you increase the deposition rate at a constant pressure of 4 milliliter, it is possible that you can increase the phase fraction of alpha as compared to the beta. So you can make a low resistive tungsten as compared to the a pure beta phase. Okay, so and we wanted to see whether it truly depends on thickness. So basically you can clearly see that 3 milliliter, okay, we deposited on 3 different substrate: glass, silicon dioxide, and silicon. In all the cases we get a mixed phase, that is irrespective of the thickness. And interesting thing is this one, that at 10 milliliter, that is at a higher pressure, even at 7, 10, 15 nanometer, or even up to 40 nanometer, you can stabilize pure beta phase by varying the sputtering pressure. So that tells us that you can have a pure beta phase above 5 nanometer. Right? So we have used the similar spin mixing conductance method, that is the spin pumping from ferromagnetic layer, that we have again used again used nickel iron as our ferromagnetic layer. And we found that spin mixing conductance at the interface is to be 10⁻18 per meter square. And using the spin Hall inverse spin Hall effect, we have found the spin Hall angle. So basically, we could by tuning the deposition rate, we could get a low resistive mix phase. In this low resistive mix phase, the spin Hall angle of this tungsten is found to be around 0.24. As compared to the literature, it is uh, higher, that is 0.17, and then we found it is to be 0.24. So with this, the summary of tungsten work, that we can see a phase transition from a mixed phase to beta phase when we increase the deposition pressure, Argand deposition pressure, due to the reduction in the kinetic energy of the atom because of higher number of collisions. And tungsten phases, we found that it can be controlled both through argon pressure and deposition power. And we can also get a beta phase even above 5 nanometer of tungsten thickness. And finally, we have shown that we can get a large spin Hall angle of 0.24 in a mixed phase tungsten. So with this, I would like to conclude that in permalloy tantalum, we have shown that we can get a phase transition as a function of seed layer thickness, and a large spin Hall angle can be shown of 0.15. And in case of tungsten work, we can see that by changing tungsten pressure and power, we will be able to change the crystalline phase, and a spin Hall angle of 0.24 is reported from this work. So with this, I would like to thank all of you for your kind attention.
Yeah, thank you. So now the talk is open for questions and comments.
Hi, Prof.
Yeah, hi, Durgesh. Yeah.
I have a very simple question. So basically, in tantalum permalloy work, the properties are better when permalloy is thicker.
Yes,
But
properties are
when
better. It is, yeah.
Yeah, but when we are going to, for example, do some switching or anything, we don't want very high, I mean, very thick magnetic layer, because
Yes,
then it
you
will
are
be a
right.
shunting effect.
Yes. Okay. So, I mean, I didn't have enough time to speak about it, but I would like to tell you that I'm not promoting permalloy here. Okay. Basically, permalloy is a crystalline material. So this work is to tell you that you have to be extremely careful when you are using a crystalline ferromagnetic layer. So let's say if you are using the standard traditional ferromagnetic layer is cobalt iron boron, so
Right.
which can be amorphous, right? Right. So even at a lower thickness, you don't need to worry about it. So this work is to tell you that you have to be extremely careful that whatever the spin Hall angle that you are measuring on a single, whatever the crystalline phase that you are measuring on silicon, that you cannot, assume that the same crystalline phase can come on top of a crystalline material, crystalline ferromagnetic material. If at all I use cobalt iron boron, it could be that I may not see this difference at all. You are right that when we are using in a, device structure, at most you want what, one nanometer ferromagnetic layer. So there we need not to worry about it. We need to worry about what growth rate that you are using to get a mixed phase, and that can help you to get a larger spin Hall angle.
Thank you.
Any other question from audience? Okay, so I have one simple question. For tantalum or tungsten case, like, I mean, you measure the spin Hall angle. So
Yes.
if I change the thickness, it is actually constant, or it's changing with thickness also?
No, so basically, when you are changing thickness, I mean, it is also related to your previous question. You or Durgesh someone asked that it depends also the resistivity. So basically, we are going to consider that resistivity also into the while measuring the spin Hall angle. So for us, I mean, in our observation, it is constant. I mean, I'm not saying that exactly constant. It is within the the error rate. That's what we found.
Okay, so a question from audience, please. Saurabh, can you hear me?
Hello? Yeah.
Yeah. Now, yeah, you can ask.
Yeah, okay. Thank you, Avinash. Yeah, hello, Professor Chandrasekhar. Nice results. So I'm just curious about the estimation of this pinhole angle as you have shown from the spin pumping measurement.
Yes.
So there you have this ISHE which has some ISHE spectra which has some asymmetry in it. So I was just curious that because when we do the STFMR also, there also we get a symmetry component. It's not purely asymmetric. So could you clarify that how you are separating this spin rectification?
So basically, this is what we are doing. So you can see that this is our ISHA signal, that is the spin pumping voltage signal,
Yes.
right? So which contains both the contributions from the inverse pinhole effect and also the spin rectifications effect, that is like AMR and ASHE. So we are only considering when we are measuring this voltage, right? We are only taking the symmetric component. So we are completely ignoring the asymmetric component that is coming into the picture. So that gives us that the results are, I mean, whatever the results that we are fitting are due to the inverse pinhole effect, not due to the spin rectification, that is AMR and anomalous Hall effect.
Okay, I see. Thank you.
Thank you.
So, any other question from audience or some? Okay, if not, let's thank to the Prof. Chandrasekhar. And after a short break, we will come at 2 p.m. for next session.
Thank you very much, Avinash, and thanks for this opportunity. Thank you.
Yeah, thanks.
Thank you.